Hello, pre-cal lovelies. In this video, I'm going to be talking about section 1.5, parent functions and transformations. With your parent functions, these are just ones that you have to know. You learned them in Algebra 1, you learned them in Algebra 2, you've learned them before. So go ahead and pause the video, copy down all four of these parent functions. Notice you have linear, and then you have the equation, quadratic, the equation, the graph, cubic, the equation, the graph, square root, the equation, the graph. Yay. That's called the monkey parent function. And here are the other two that you should already know. This is the reciprocal function, the function, and the graph. Absolute value, the function, and the graph. Okay, again, just pause the video, copy those down, make sure you have the points in the right spots, and then we will talk about the greatest integer function. All right, for the greatest integer function, that is that symbol right there. It almost looks like a double absolute value with kind of like a bracket inside of it. What I usually do is I will draw a bracket, and then I will put a little line really close to the bracket, and then it's just the same thing on both sides, it's just opposite. So this is equivalent to the integer below the value of x. So for instance, if we are looking for the greatest integer of 4.7, well, that would just be 4, because it will round down to 4. Remember, integer just means whole number. I need a different color pen. Whole number. Okay, and the greatest integer of 13.2 will just be 13. It's kind of when it gets to the negative numbers that you have to be careful. So negative 6.7 will round down to negative 7 because that is the integer below it successively on the number line. So if you're at negative 6, and you have negative 7, negative 6.7 would round down to negative 7. Likewise, here's 4, here's 5. 4.7 would round down to 4. So you're just pretty much rounding down the entire time that you are working with the greatest integer function. So let's take a look at the graph. All right, here's our greatest integer graph. This is your parent function graph. Okay, notice I have f of x equals the greatest integer of x. So with each of these, let's look at these one at a time. So it looks a little bit crazy. I mean, I know there's a lot on the page. It's something brand new to you guys, I understand. But bear with me. If we are at 0, the greatest integer of 0 should be 0, right? Because that is the number below or equal to 0. And the greatest integer of, say, 0.5 would be 0. The greatest integer of 0.9 would be 0. But as soon as I get to like the greatest integer of 1, it's going to jump up to 1. So there's a ton of jump discontinuity here. So looking really close, see if I can zoom this in really close. Really close. Whoa. Super duper close. My finger is giant on your screen. Squishy like a bug. I can't even fit both fingers. A squish. A squish. Ah. Okay. So from 0 to 1, all of the numbers in between there, because they're all going to be decimals like we had over here, they're all going to round down to 0. So those are all rounded down to 0, so that's why the y value is 0 for that whole thing. Once you get to 1, it jumps to 1. And then 1.2, 1.3, 1.4, 1.5, 1 point anything is going to round down to 1. So again, that is why the y value is 1. Same thing for 2. 2 point anything will round down to 2. 3 point anything will round down to 3. Right? Same thing in the negative direction. So pretty much as long as you have the first pattern kind of established and you know how those are supposed to look, it just repeats the same pattern to infinity in both directions. All right, next thing I'm going to talk to you about is all the transformations on the parent functions that we could possibly make. What transformations mean is just how our parent functions move around, whether they vertically stretch, whether they horizontally shrink, whether they move up, down, left, right, whether they flip over the x-axis, reflect over the x-axis, whatever they do. So this is a quadratic parent function because we have a squared function. It works for any parent function. I'm going to refer to these things as if I am inside of the parentheses, that I am inside with the x. Anything on the outside, which I will underline in blue, so I consider a to be on the outside, and I consider the plus or minus anything like that to be on the outside. Outside is going to change things in the y direction. Okay, so everything on the inside with the x will change in the x direction, left and right. Everything on the outside with the y, that includes our a over here, will change it in the y direction. Okay, so I'm going to define a few things. So let's see, if we have a, this is going to vertically stretch or shrink. If a is negative, it reflects it over, take a positive y, make it a negative y, the x-axis. Okay, I'm going to take a second and write down the inside part so you don't have to listen to me talk to myself as I write things because it's a little bit weird. Okay, magically poof. Here's the rest of it. B is a horizontal shrink or stretch or shrink, so we will multiply the x values. If B is negative, it will reflect. Yeah, I'm out of school. See you guys later. Nah, not really. I'm sorry. I'm just joking. It wasn't even a funny joke, but that's okay. You still smiled at how awkward you felt. Anyways, if B is negative, it is going to reflect it over the y-axis. H will move everything left and right. So again, notice that everything on the inside of this affects it in the x direction. Everything on the outside will affect things going in the y direction. All right, so I'm going to look at our first example. And also with these, in order to transform functions, so to transform, we have to think about Mrs. Backwards.
Hello, everybody. I'm Mrs. Backwards. I have a lovely husband at home. He feeds me apple cobbler, and I like to eat apple cobbler. So the way you spell Mrs. is MRS, so Mrs. Backwards is SRM.
Thank you, Mrs. Backwards. Okay, so these are basically the order of transformations. The S stands for stretching or shrinking, which really is just talking about multiplications of any kind. So if you have to multiply. Okay, the R stands for reflections, which is just talking about negative signs. That little symbol there means negative minus VE. It's Mr. Khan's symbol, so if you have a problem with it, talk to Mr. Khan and he will have some words. M stands with move, for move. So this is like left, right, up, or down. So that is if you see a plus or a minus sign of any kind. So in this situation, my parent function, it kind of looks like the reciprocal, f of x equals 1 over x. So that's the parent function that I'll be moving it from. I have a plus 7 with the x, so the move in this instance, let me grab another colored pen, would actually be to the left 7. If you are with your x, x plus 7, x is 7 with x, you're going to do the opposite thing of what you think. So you see plus 7, usually plus, you go to the right, but you're going to do the opposite and go to the left. Ooh, look at that ink. Ooh. Okay, the other thing we have is minus 4 on the outside because it is not with the x, so we will go down 4. Okay, so let's actually do that. All right, so when I am graphing these things, I always start with my parent function. So in this case, I have the reciprocal function as my parent function. So I have my parent points at 1 and 1, I have the 1/2s, the 1/2s, and I know what the graph is going to look like. Then I'm just going to take everything, move it left 7 and down 4. So from center, since I know that's where my asymptotes are, I'm going to take them and move them left 1, 2, 3, 4, 5, 6, 7, down 1, 2, 3, 4, and that is kind of where the new origin is, or where it has moved to. So I have asymptotes here, and coming out that way and going that way. And then same thing, if I took this point and moved it left 7, down 4, this would end up right there. Same thing, take this point, move it left 7, down 4, left 7, down 4, and then there is that part of the graph. Okay, same thing on the other side. I would take this point, move it left 7, down 4. It's kind of off the graph, but we can still put it on there just to show you guys what it's going to look like. Be about right there. So everything has just moved left 7 and down 4, and there would be your new function. All right, looking at another one. This is our absolute function, absolute value function. So my parent function is f of x equals the absolute value of x. So the changes are that negative in front, the 2 in front of the x, and the plus 1 on the outside of the function. So stretch, reflect, move. I will always list that out to the side. As far as stretching and shrinking goes, this is multiplying the x by 2, but again, remember that with your x's, you are going to do the opposite of what you see. So we are going to do the x's by 1/2, which is actually going to horizontally shrink my x values. I also have a negative multiplying with the x, so I'm going to reflect over the y-axis, and then up 1, because I have plus 1 on the outside. All right, let's graph it. All right, so here we go. I like to use a lot of different colors with these. Kind of helps me see the different moves that it's going to make. If you want to use colored pencils, feel free to, whatever you want to use. Okay, so first, again, remember that this is the order of transformations.
Yeah, remember the order of transformations.
Thank you, Miss Backwards. I'm glad to know you are still here. Okay, so I'm going to stretch the x's, multiply the x values by 1/2. So this x value is at 1. Well, 1 times 1/2 is 1. 2 times 1/2 is 1. Sorry, that's supposed to be 1/2 down there. I lied. 3 times 1/2 is 1.5. So I can see that the pattern that it is making, these just get twice as close to the x-axis. So, oops, I messed that one up. So it kind of just shrinks the graph. It makes it squeeze a little bit to the inside. Okay, then I can flip it over the y-axis. Well, in doing that, if I take everything over here and I reflect it over the y-axis, it's actually going to map onto itself, so we won't be able to see anything happen when we flip it onto the y-axis because there's already a line there. So just kind of rotate that in your head and yay, we did it. It maps, and if I flip this line over here, it goes there, and if I flip this line, it goes there. So there's already stuff in that place, so we don't really have to move it that much. Okay, and then my last step, I will take everything and I will move it up 1. So I'll take this point, move it up 1, move this up 1, up 1, up 1, up 1. So there's my pattern established of my final graph. And then it's just a matter of drawing it. Connect the dots. And there would be your final graph. And again, if you guys are going to do the different colors, that's cool. Just make sure I know which one is your final graph. I prefer to keep dotted lines throughout because usually I just took my tests in pencil, so I always use dotted lines until my final graph I would make a solid line like you see here. Cool. Alright, here's the last one that I'm going to graph with you guys in this video. If you have any other questions, please ask your teacher or come ask me. I promise I will help. So with this one, we have a quadratic function, so that is my parent. I have a -2 on the outside, so I'm going to reflect this over the x-axis. And I'm also going to multiply my y values by 2. I have a +1 on the inside, so I'll move this to the left 1. Okay, again with the opposite, same thing. If it is with the x inside, it is the opposite of whatever you see. So like the last one, how we shrunk it by 1/2. This one we're going to move it left 1. On the outside of our parentheses we have a 2. So if it's on the outside, just do whatever you see. So you will multiply everything by 2, and then you will flip it over the x-axis. Alright, so again, make sure you follow the order of transformations. First we are going to stretch and multiply the y's by 2. So here my y value is 1, 1 times 2 is 2. Here my y value is 0, 0 times 2 is still 0. 1 times 2 is 2. 4 times 2 is 8, and 4 times 2 is 8. Oops, that's 7. So these are going to be up here, I'm sorry. Ignore those, ignore. So here is the new graph so far. Remember that is only after we multiply the y values by 2. Then I'm going to flip this over the x-axis. So all of the points that were up here move to the same position, but just across the x-axis. So that one will stay the same. So now it just looks like a mirror image of the graph. And then take all of that and just move it left one. Oh no. We did it again. And there you go. There would be your final picture. Now I guess I have to go teach real class. See you in a second. All right. It's actually the next day. I was lazy, so I didn't see you in a second. I saw it. Whatever. It doesn't matter. I'm seeing you right now. It doesn't make sense. The next piece there we are going to look at. This is called a piecewise function. Piecewise function. Piecewise. So all that means is there are two different pieces. You've done this before where you've had to calculate the values. Notice, like always, you only have the function x minus 2 if x is less than 0. Well, that would only be that side of the graph. And we only have the function 2x plus 1 if x is greater than or equal to 0. So that's going to be that side of the graph. Now, in order to graph these things, remember these are both your linear parents. So x minus 2, I would cross at negative 2, but notice it is not equal to 0, so I will put an open dot at 0 because it is only less than. Okay, remember that's just your parent graph moved down 2 for your linear function, so then I can continue to do the other side of this graph. And there is that part of the piecewise function. Okay, only when it is less than 0. Yes, there would be a part that continues that way, but I chop it off since it is not a part of my domain. Okay, for the other side of this function, I have 2x plus 1, so I have a y-intercept of 1. Then I go up 2 over 1 to graph it. And this line is continuing that way, which makes it so that we have a jump discontinuity. There would be your graph of your piecewise function. Because x is greater than or equal to 0, we have it this side, and when x is less than 0, this function exists on that side of my graph. Cool. All right, I'm going to be looking at another piecewise function. I have the function 3 if x is less than 2. So it looks like at 2, what I consider this to be kind of my boundary point. That's where the graphs kind of split, because I have it when this one when it's less than 2, this one when it's greater than 2. So at 2, that's where I'm going to kind of see that division. So if it's 3 all the way up until 2, but not including it, then I will have an open circle at 2, and it will go for 3 for infinity and beyond. Okay, negative x squared plus 8, well, that's a parabola that is flipped down and that has moved up 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I have kind of that point, this point, over 2 down, 1, 2, 3, 4 will be my first point. 1, 2, 3, 4, 5. And then I have a parabola going straight down. That is the part that I can see. And it's actually really just that. But yeah, pretty close. And there would be your piecewise function for that one. Sorry that this is turning out to be such a long video. I'm almost done, I promise. Give the equation. So we are given a graph in this situation, so we are finding an equation. So it looks like my parent function is the absolute function, and it looks like it has moved to the right 3. The way to do that is to make it with the x on the inside. So to make it go to the right 3, you've got to do the opposite, so x minus 3, absolute value. That looks like all that happens to my function. It doesn't move up or down. It doesn't multiply in any way because I can see it still has the same parent points. And there would be your equation. All right, last example for the day. Giving the equation of this function. Your parent function here is a square root function. So it looks like it has flipped it over the x-axis. So if it's on the x-axis, that means it was on an outside negative. And then if it has moved left 2, I can do the opposite with the inside. So there would be our function pretty much. I'm just going to rewrite it down here. Negative square root of x plus 2. That flips it over the x-axis. Plus 2 on the inside moves it to the left 2. Didn't multiply at all because, again, I still have the same parent points. Hopefully this video was helpful for you guys. I'm sorry that it was so long. I will try to keep them short in the future. Love you guys. Bye.